Hi, we've got another video on the GPS disciplined oscillator today. So this is probably going to be the last in the series on this unit. I'm hoping to get this completed today. So in the past few months I've designed a circuit and got some PCBs made, so we'll have a look at those in a moment. I've also had a new front panel made. So we've got a front panel here with the cutout for the vacuum fluorescent display. There's also a hole for a DB9 connector for the RS485 interface. So we're going to assemble the unit with all of the circuitry inside, and then we'll try and flash the firmware on and see if it all works. So I've not really done too much on the firmware. I've just added the code to enable the RS485 output. For now I've not done anything on the 2.4 GHz Zigbee interface because I need to work on that for the lighting project, so I'll probably add it in at that point. So let's go down to the bench, we'll have a closer look at the schematic and then we'll have a look at the PCB and then we'll start building the circuit. So here we have the schematic for the GPS disciplined oscillator PCB, and this is going to be available on my website. So if you click in the top corner here with the little eye is, you can follow the link to my website and download this as a PDF. So in the top left hand corner here we've got the power supply section. So if you recall from the previous video, the GPS disciplined oscillator unit was designed for telecommunications use, so it required a 48 volt supply. So rather than modifying the GPS disciplined oscillator too much, I've decided just to stick with the 48 volt supply. So we've got the header for 48 volts, we've got some reverse polarity protection and some filtering, and then I'm just using one of these XP Power 48 to 5 volt DC to DC converters. This was quite cheap and it was a lot easier than me just laying out a circuit on the board, so I decided to go with one of these. And then we've just got the a bit of bulk capacitance on the output of that. And then the circuit hasn't changed too much from when I was prototyping on the breadboard. So we've got a DSPIC 30F3013, which is a older style 16-bit processor that still runs on 5 volts, so that means I can interface with the vacuum fluorescent display nicely, and also with the serial interface from the GPS disciplined oscillator. So we've got the PIC in the middle, we've got the in-circuit programming header on the left here, we've got a 10 MHz crystal attached to the crystal inputs on the microcontroller, and then we've got the output here to the vacuum fluorescent display and the input from the GPS for the time of day input. And then just on the right hand side here we've got the RS485 interface, which I'm going to use to interface with the clock in my lab, and then we've just got a transceiver here for converting the levels. So that's all fairly straightforward. We've got a few diagnostic LEDs just to help with debugging, and then the new addition, which I haven't prototyped prior to laying this out, so we'll see if this works at some point in the future. So we've got a MRF24J40MC, which is one of Microchip's 2.4 GHz wireless transceivers, and it is part of Microchip's 2.4 GHz kind of wireless system. So I bought a Xena, which is the USB interface for capturing packets on your PC. I haven't actually tried using this very much yet. I did use it on the Explorer 16 briefly, and it did seem to work okay, so I just thought I'd go with that. The modules are really cheap, so that was the main driver for using those. So these transceivers do run on 3.3 volts, so we've got a linear regulator here for providing the 3 volts, and that just feeds directly into the transceiver. And then we've got a logic level translator here, so this is a bidirectional model, and this just converts the 3.3 volts to the 5 volts that we need for the microcontroller. And then we've got another new bit of circuitry in the bottom right here. So this is an amplifier, and if you recall from the previous video, the GPS disciplined oscillator only had a 2.048 MHz output on the back of the unit, and I want a 10 MHz output so that I can feed it into the various bits of equipment in the lab. So the idea is that this PCB is going to attach directly to the GPS board, and then we're going to tap directly off the ovenized oscillator output, so we'll get the 10 MHz directly, and basically all we're doing here is just amplifying the output and feeding it into a 50 ohm termination resistor, and then we're going to have the 10 megahertz output on the back of the unit. So there's nothing too complex here. We've got a couple of resistors here biasing one of the inputs to the op-amp at half rail, and then we're capacitively coupling in the 10 megahertz input, feeding it through a non-inverting amplifier with a bit of filtering here, and then we just feed it straight out to a BNC connector. So here's the PCB that I've had made. I had this made at a place in China called Elecro. So I went on the PCB Shopper website, which compares quite a few different manufacturers of PCBs, and had a look. This place wasn't the cheapest, but it was certainly very good value. So I had 5 of these PCBs made, and I think that was about £15 without shipping. But the reason it's been a bit quiet is I've actually had quite a few PCBs made for various projects that I've been wanting to do. So I've got a whole box of boards here. We've got the LED driver PCBs here. I've got loads of those made. I don't know what I'm going to do with all the boards. And then we've got a few other projects which I've been wanting to do. So I think I've spent about £200 on PCBs, which is really good actually, because if I'd had this board alone made at PCB Train, which is where I normally get my boards made, this board alone probably would have cost about £80. Shipping was about £30 with DHL, and I think there was an import fee of around £40, but overall still a lot cheaper than it would have been to have made over here, and the quality is really not bad at all. There's nothing too challenging on this particular board, but the it seems really well made. The solder mask quality is pretty good. This board has the hot air solder leveled finished, although I did get a few made with the gold finish because they've got battery contacts on. But yeah, these are really good. I'm quite happy with these. Obviously I haven't tested them yet, so there could be some surprises waiting, but today we'll find out whether this board is working. So just having a quick look around the board here, we've got the 48 volt input at the top left here. We've got these capacitors before we get to the DC to DC converter. We've got the 2.4 gigahertz transceiver up here with the voltage regulators. We've got the PIC and the in-circuit programming header here. The outputs to the vacuum fluorescent display and the input from the GPS. And then we've got the 10 megahertz amplifier just here. And unfortunately I have noticed a mistake, and annoyingly that was about 24 hours after I sent off the PCB file, so it was too late. They already started production. They're actually very quick at getting these boards made. I think it arrived certainly within 2 weeks of having the boards made. I think it was actually 6 days or something like that, which is really quite impressive. But the in-circuit programming header is not going to work on this board, which is really annoying, because they offer alternate pins, but it turns out that these are for emulating and debugging only. You still have to use the original PGC and PGD pins for programming. So I'm not really sure what use that is. I don't know if the microchip ICE has an additional interface for those 2 pins, but certainly for the ICD3 and the other programmers, you can't use the alternate pins like you can on the DSPIC 33s, which I'm used to using, so I was expecting the same kind of setup. So I've connected the header to EMU-D and EMU-C3, but it looks like we're going to have to cut the tracks on there and join them on to PGC and PGD. It shouldn't be too bad. We should be able to break the tracks here and then just connect to the track on this side, and there's one on the other side, so it shouldn't be too bad. But we'll get started with assembling the board and we'll see how we get on. Right, so here we have the assembled PCB. That wasn't too bad. I decided not to film it and just get this done as quick as possible. It was a little bit of a pain finding all of the components, because basically I've ordered all of the components for all of the projects, although it was 3 different orders from 3 different places, so it was a bit of a pain trying to find the individual components, as some of them are duplicates across all of the projects. But I think that's probably taken about an hour, which isn't too bad at all really. So I've not put the DC to DC converter in because I want to attach this to the bench power supply the first time it's powered up. and you can't really do that with the DC to DC there. So I've soldered on some flying leads to where the 5V output would have been, and we'll connect that up to the bench power supply in a moment. And then we've got the PIC here and one of the bodge wires for the programming header on this side, and then we've got the other one on the other side. It's a bit annoying that I've had to modify the PCB, but the result's not too bad, so I'm not too concerned. And then you can see we've got the RF module here, and that's got a little UFL connector. So I've got a 2.4 GHz antenna with a UFL connector on the end of it, which will go on the front panel. And then we've got the RS485 output and a header here for attaching the 100 ohm termination resistor. And then we've got a RF connector on the bottom right here, which is going to connect to a cable which goes to the back panel of the GPS unit for the 10 MHz output. And then we've got the 16-way header which goes to the vacuum fluorescent display. So that should match up with the connector on here, although when it comes to mounting this actually in the unit, there's not enough room for the height of all of this, so I'm going to have to either solder the ribbon cable directly onto the PCB, or since there's only about 4 or 5 wires used actually on the interface, I might just connect up the header a bit like I did on the breadboard in the earlier video. And then we've got a 2-pin header here for the serial interface to connect to the time of day output from the PCB. So I'll attach all the equipment up, so we'll attach the power supply and the in-circuit programming header to the ICD3, and we'll see if we can get this board working. I'm not going to program the RF module today because, as I said earlier, this is going to be very similar to the code that I designed for the lighting controller, so I'll wait until that point to get this module working, although I have played with this on the Explorer 16 board just with some demo code, and it all seems to work okay. So the firmware hasn't really changed, as I said earlier. The only addition is the RS485 output, but I've actually designed the circuit the same as when I breadboarded it in the previous video, so it should really just be a case of flashing the firmware on this PCB and it should work exactly as it was before. Right, so I've got the bench power supply connected to the 2 wires here. I've got the Fluke 87 with the ground lead connected to the power supply, and then I've got the other probe. So we'll try turning it on. I put a 100 milliamp current limit on the power supply, and yeah, it's drawing about 70 milliamps. It's a little bit high, but the RF module I think has a reasonably high quiescent power draw. So we'll just check. We should have 5 volts on the input here, which we do. We should have 5 on the memory clear pin and 5 on one of these power supply pins, which we do. We should have 3.3 volts up here. Yep. 5 volts on the op amp, which is on pin 7, I think. Yep. And we should have the mid-rail supply also. Yeah, which is about 2.5 volts. So that all looks okay. We've got no smoke coming out and it's drawing a reasonable current. So we should be able to hook up the ICD3. And we've got the blue light on the ICD3, which means that it's detecting power. So I think we'll just go for gold here and just try programming the board. So it's picked it up okay, and it's programming now. Programming done. So we should be able to remove this. Yeah, and you can see we've got one of the debug LEDs illuminated. It's quite bright in here, you may not be able to see that LED, but yep, so that seems to be running. So I guess the next thing to do is hook up the VFD and see if we get an output on the display. Right, so I've hooked up the vacuum fluorescent display and I think we'll just go for it. We'll try turning it on and see if it works. Oh right, we've still got the current limit on. So the vacuum fluorescent display has a boost converter on the board to generate the high voltage. So it does have a reasonably high inrush current, so I just need to increase that on the power supply and we'll try turning it on again. Right, and there we go. Yeah, we've got text. Yeah, that was easy. As I said, I didn't really change the circuitry too much, so it would have been a surprise if it wasn't working. And the baud rate should be correct for the time of day input, considering that the vacuum fluorescent display has a UART interface. So if the crystal was out or something like that, we wouldn't be getting any text on here. So that all seems to be working okay. We could test the 10 megahertz amplifier. I'm inclined just to put this on the board and try it with the oven oscillator, and then if it doesn't work, these components are easy to access and we can work out what's wrong when we put it on the board. But we may as well just attach this to the PCB and see how it goes. I can also put the 48 volt DC to DC converter on the board now. There's certainly no dead shorts, and that's the only reason that I was worried about putting the converter on there. So I'll solder that on, and then we'll have a look at how we're going to assemble this onto the main PCB. Right, so I've just soldered the DC to DC on the PCB. That fitted perfectly. I was quite happy with that. It looks overall quite neat. Hopefully the rest of the circuitry is working okay, but we seem to be having some good fortune so far, touch wood, so I'm quite confident that we should be able to have a fully working unit by the end of the day. So the idea is we've got the GPS disciplined oscillator board here, and we've got the oscillator underneath the polystyrene here. But the idea is that we've got a couple of holes in the board here, and I've put two holes in the same place on this board, and we should be able to attach some screws through this PCB and hold this board in place. And then if you recall from, I think it's the first video on this unit, we've got the 10 megahertz output just here and the 0 volts just here. And I've correspondingly put one hole here for the 10 megahertz and one hole here for the 0 volts. And if we attach some solid core wire to each of these two pins, we should just be able to slide the board down, and that will get us our 10 megahertz signal onto this PCB and also the 0 volts. And then we can just route the amplified 10 meg out to the back. I'm slightly worried that this side of the board is unsupported, so we'll have to see how well these two screws hold this board in place, because actually the heavy parts are on this side of the board, which is not ideal. So I may have to either attach or put some glue underneath to hold this in place, or see if there's some way I can support it from underneath. But we'll put the screws through and see how well and how flimsy this thing feels. Right, so I put a little bit of flux on these two terminals here. I might add a little bit more solder. Then I've got some solid core wire. This is just tinned copper wire. That's one. And that's the ground connection. So I'll just try and find some screws to go through here, and then we should be able to place the board on top. Right, so I've grabbed some 20mm M3 screws, and I've got a couple of spacers here. I think these are either 4 or 5mm, so we'll put those over there. And then on the PCB itself, I've just put a nylon screw and nut, just so that if it is moving around, it doesn't accidentally short out onto this PCB. I still need to see if we need some kind of support to stop it flexing in this direction, but at least it can't accidentally hit the PCB now. So we should just be able to try and slide this board over the two wires and onto the M3 nuts. So I'll see if I can line those up. That seems to be okay, so we'll put some washers over the screws. and then I've got some nylock nuts, so these shouldn't come undone. So I'll put those over the top there. And then it looks like I'll need to support the screws underneath to get these done up. So we'll tighten these up and this should all be attached in place. Right, so we've attached the PCB now, and I've also just soldered the two wires very carefully so as not to disturb the joint actually on the main PCB. It seems really well attached actually. I'm tempted to just leave this as it is. It doesn't seem to really be flexing at all. So now we can wire up the PCB to the main board. In advance of this video I soldered a wire onto the RS232 transceiver down here, so you can see I've fixed a little wire onto the TTL input to the MAX232A and fed that through the PCB, and that appears on the other side of the board just here. So I've glued down a little 2-pin header, and one of the pins here is soldered onto the ground plane of the PCB, and then the other one is obviously the signal which goes through to the second pin. So we can connect up the cable which I've already made, so this should just plug in onto this header on the GPS board, and then we should be able to bring this onto the 2-pin connector for the time of day input. So I'll just check so I've connected that the right way around. I've created a 9-pin D-sub connector to 3-pin connector for the RS485 connection. We'll deal with that a little bit later on. But I think next we need to wire up the power for the unit. So I didn't really want to be modifying the power supply circuitry on the GPS board too much. I've decided to stick with the 48 volt power supply that board needs, and also I added the 48 volt DC to DC on my PCB. So what I've done is I've purchased a 48 volt power supply. So this is a 230 volt, it's probably universal actually, mains input to 48 volt power supply. This is 48 volts at 2.2 amps, so that's what's that, 100 watts, the MSP 100-48. This is made by Meanwell, and it's actually a really nice quality power supply. They've used Nippon Chemicon capacitors in here. They're all glued down. The construction is really nice all the way throughout. It's a really nice unit, so relatively inexpensive. I can't remember how much I paid for it, but it wasn't too expensive. But it's a really nice unit, and the idea is that this is just going to screw into the chassis down here. So I've already drilled a couple of holes for it in advance. And then I've got an IEC connector which is fused, and that will go on the back panel and wired straight into this unit. So no power switch. I shouldn't need to turn off the mains once it's plugged in. And you'll also see I've drilled a hole here. So this is a 20mm hole, and that's the same size as one of these rubber grommets which you can fit from the outside. And the idea is that when this PCB is in place, and so it goes this way up, when this PCB is in place, the in-circuit programming header should line up with this hole, so that when I need to update the firmware, so I do need to update the firmware at some point with the 2.4 gigahertz transceiver stack, I can just do that from the outside without disassembling the unit. So I should just be able to pull out the grommet and plug in the header from underneath. Whether the measurements are correct, I don't know. I haven't put this in place to have a look if I can see the header. It looks to be about right, and I did measure it a couple of times, so that'll be quite a nice feature for the future. So what I'm going to do next is wire up the power supply. I'll use some crimps and everything to make it nice and tidy and safe, and then I'll rejoin you after I've wired all of this up. Right, so I've screwed in the power supply. We've got the mains connections here with some 1.5mm brown and blue cables with some spade connectors on the end, which will go into the IEC connector. And the same for the earth, which also goes to the chassis screw, as well as to the earth terminal on the power supply. So the IEC connector itself has a fuse holder. It's not internally linked out, so you have to bring out the live conductor from the IEC connector into the fuse holder, and then the live comes out the other side. So that's going to be mounted on the rear panel, and it will probably end up coming through this hole here, and then we'll be able to plug in the spade connectors. And then we've got the 48 volt out supply for the GPS board here. So I've made a little connector from a 2-row header because the GPS disciplined oscillator board had this daughter board with the power connector. So I've just worked out which pins are connected to what and made something that can plug into the board. And then there's another set of cables which come off the 48 volt supply into my PCB, and this has some bootlace ferrules on the end just to stop the any strands of wire coming off. So I think what we'll do now is tackle the 10 megahertz output. So the idea is that all of these connectors at the end are unpopulated and not connected to anything. So I've got another BNC connector which should fit into these holes just as these two do, and I'm going to connect a piece of coax. So I've got one here with the correct right angle connector to plug in here, and then I'm going to trim this off and solder it directly onto the pin for the 10 megahertz output on the BNC connector, and also to ground. So I'll just try and do that now. I've already cut a hole in the back panel for this, and then after that we'll have a look at the front panel section. So unfortunately it doesn't look like my plan's quite going to work, at least today. This is the connector which I've purchased, and it's a different height off the board. The only other type I've got is the one with plastic, and again that's still the same height as these. So I think what I'll do is, I've had a rummage around, I found a kit here for a connector, and this is a bulkhead mounting BNC connector, and it connects directly to the wire instead of to the PCB, so this should be able to fit in here. This is the cable I've got with the connector to attach to my PCB, but it does mean that this will be mounted directly to the rear chassis panel instead of to the PCB, but I'll try connecting all of this up. You have to assemble all of these parts into the BNC connector, which might be fun because I've got no part number for this, but it should be reasonably self-explanatory. Right, so I found a connector online which looked almost identical. So this was made by Telegartner. So I'm assuming this is the same part. I did end up with one spare gasket, so I don't know if that was accidentally packed into the bag or whether I've missed one out, but everything seems to be holding nice and tightly. The inner terminal is all in there properly and there's no shorts or anything. So I think the idea is that I'm going to kind of just sit this in the right kind of place and bring this round to the connector that's underneath, and mount it to the panel once it's all in place. Right, so the final thing that we've got left to do is to do the front panel. So I decided to scrap the original front panel for this unit and have a new one made. So I had this one made at Schaefer AG. So if you go to their website, you can download a utility which you can design your front panel in. You choose the thickness of the material, what material you want, the finish that you want, and then within the program you can do all your holes, cutouts and any lettering and everything like that you want doing. You can choose from a whole load of finishes, although because I chose to have the lettering printed rather than engraved, that limited my options to plain silver or plain aluminium only, but you can choose anodized black and all other kinds of finishes. So the tool's really good. You can design all of your cutouts and everything like that, and then within the program you can bring up an order form which gives a breakdown of the price of all of the different cutouts and that kind of thing, and then from within that program you can place the order. And from Germany, I think this took 4 days. I didn't pay for premium or anything like that, but it came really quick. And then I also had some acrylic cut. I'm not going to take it out at the moment because I don't want to get fingerprints on it, but I had some acrylic cut to fit the inside of this. And within the program, if you make a mark that says that you want the acrylic to fit within the aperture, they basically guarantee that it fits perfectly with a press fit, so you don't need to use any adhesive or anything like that. I'll just be able to push this in the hole and it should stay where it should be. So the vacuum fluorescent display is going to go behind the acrylic panel in there. We've got the DB9 connector for the RS485 connection, which I've already created a lead for, and then finally in the top we've got the antenna, which is going to slide in that hole. And I also got some 4mm holes cut, and I had some acrylic rod which was 4mm in diameter, so basically I cut those myself and pressed them in, and they're pretty much flush with the surface, so those will form kind of light pipes for where the LEDs are behind here. So what I need to do now is try and get the vacuum fluorescent display attached to the front panel. I don't think I'm going to be able to use the connector which is on the vacuum fluorescent display because there's not enough clearance between where the display is and the PCB back here. So I think I will create a new cable and just solder it in onto the vacuum fluorescent display, and then we'll be able to plug it into the PCB. So I've got some more of these vacuum fluorescent displays. I don't really want the red filter on this, and I tend to use this one just for playing around before I use one of the brand new ones. So I think I've got about 3 more of these, so I'll dig one of those out. I still need to remember to make the changes here for the baud rate and the UART and everything like that, which I did in the second video. So I'll do all of that, and then we should be able to wrap up. So I think that's everything that I'm going to do today. So I already cut out a hole for the IEC connector. It's a little bit wonky, but it is covered by the bezel. So that's going to go in the rear panel like that. I've also cut a hole for the 10 megahertz output, and then I think one of these grommets should more or less fit in this hole here as well to blank up the power connector that was there before. So I'm going to do all of that and then assemble it all together, and we should be able to test to see if it all works. Right, so here we have the completed front panel. I've put the acrylic in the aperture, and then I've got some ND gel. This is lighting gel from Lee Filters, just to give it that dark appearance. And then I've mounted the vacuum fluorescent display behind that. There's a little bit of tape just holding that ND filter in place, but actually once the vacuum fluorescent display is tightened up with these nuts, it presses against there and holds it all in place. And then I've got the connectors here for the RS485 and the little UFL connector which goes to the microchip 2.4 gigahertz transceiver. And we should just be able to attach this to the front panel. I was hoping to use some different nuts, but it looks like these are a strange thread. I don't know if these are imperial thread or something like that. So fortunately I kept all of the screws from before, so we should just be able to attach the front panel back to the front of the unit and then start assembling the device. Right, so I've put the unit back together now. Just the top cover is the only part remaining. I'm going to leave that off for now. I haven't tested anything yet, so I'm really hoping that it all works as it did before, because otherwise there's quite a lot of screws to get back to the board. One thing I didn't mention was that I tidied up the filter that was here before. So when I realised that this GPS module was designed for 12 volt GPS antennas, in the first video you'll remember that I just placed a inductor between the 5 volt supply and the supply to the GPS antenna. What I've got here now is a pair of ferrite beads, a film capacitor after that, and then we've got an LCL EMI filter, which should really clean up the signal and stop any GPS noise getting back into the main board. So I'll just go and find a mains cable to plug this in, and we can see if it works. Right, so I've got an IEC connector in here. We've got the GPS cable which is coming from the antenna outside, so we'll plug that in. Right, and let's try turning it on. Right, so it's saying awaiting satellites. It's got the flashing red LED. So we can leave this just to see if it can find a lock on the GPS satellites, and then we should get the time and date on the display if it's all working correctly. So I'll just leave this until it hopefully locks onto some satellites. Right, so it's still finding satellites. It has found some. The green LED is on, but it's not done the correction or found the time yet. So while it's doing that, I just thought I'd show you what the rear panel is looking like. So here we have the back of the unit. It's pretty much the same as it was before. So we've got the antenna connector on the left, we've got the 1 pulse per second and the 2.048 megahertz outputs, and then this is the new connector which I just added for the 10 megahertz output. And actually we can still test this even though it's not locked onto satellites yet. The oven oscillator is obviously running the whole time, so we will get 10 megahertz out. It will just not be in phase perfectly with the GPS. And then we've got the two serial outputs, the new IEC connector for the mains inlet. We've got a 2 amp fuse, which is on the 48 volt supply. We've got a power LED. This is a blue one specifically for my colleague at work. He loves blue power LEDs, so Rob, if you're watching, that's for you. And then I've just got to plug up this hole. So one of these rubber grommets does kind of sit in here. It just needs a little bit of glue to stop it falling out, because although it would have fitted through the aluminium faceplate, it hasn't got enough depth to go all the way through both of the holes. So that's the rear of the unit. We can give the 10 megahertz a test, so I'll just set up the oscilloscope and then we can have a look at what the output's looking like. Right, so here we go. I've got the Rygold connected up to the 10 megahertz output. We've got a T piece here with the 50 ohm terminator, and we've got a nice 1 volt peak-to-peak sine wave output. It's slightly misshapen. That could well be due to the T piece or just the BNC cable, but it's doing its job. It seems to all be working correctly. If I take off the 50 ohm terminator, we double in amplitude, so the 50 ohms is correct on the output of the amplifier. So that all seems to be working correctly. So now I just need to wait for it to lock on to satellites. Actually, it's on solid green now, so we'll just turn it around and have a look to see what it's looking like. Right, so we've got the solid green LED on, which means that it's locked onto the satellites correctly. We've got the time, which is coming up to midnight, and the data which is coming from the GPS unit on the bottom line. It looks like I've done something wrong with the real-time clock code. It is Saturday the 8th, 2015, but it's August, not October, so I'll have to have a look at the code to see what I've done wrong there. It may be just that I got the months mixed up in the array. I'll have to have a look and see what's happened, but it's got the weekday and the day and the year correct, so obviously I've just mucked something up there. But other than that, it all seems to be working correctly. And the front panel, I think, looks really quite neat. They've done a really good job of producing a high quality front panel, and the printing quality on the front is also really nice. So if you ever need to get some front panels made and don't really want to do it yourself or don't have the equipment, I would recommend using Schaefer AG. I'll put a link in the description down below. And yeah, we've also got the antenna. So this has a little screw-on antenna which will be for future use, for distributing the time around the house, and then the RS485 connection, which is going to interface with the clock that I've got in here. So I don't think I'm going to do any more videos dedicated to the GPS unit unless there's a major update for some reason. I've still got the 2.4 gigahertz interface to implement, but the lighting project will have the same transceiver on there, so I'll probably incorporate that into the lighting project with the constant current LED driver. And the interface to the clock through the RS485 connection, I'll probably just do on the side, and then you'll see it updating the clock directly when it's fully implemented. But overall, I'm quite happy with how this looks now. I've got to find space for it. I'm actually running out of space quite a lot. and I'm actually trying to sort out the house a little bit. Part of that is the server that I'm running, so it's been a bit quiet recently also because I've been trying to sort out all of the networking and the server that I've got in the house. So at the moment I'm running a Dell PowerEdge 2900 revision 3 with a pair of quad-core Xeon processors and 32 gigs of RAM and a whole bunch of hard drives in RAID. But that unit is really kicking out loads of heat at the moment. I think it draws about 350 to 400 watts continuously, and particularly in the summer it's just making the house really quite hot. And I also need to sort out the network cabinet, which is a real mess at the moment. It was quite tidy, but I've recently transitioned from analog CCTV cameras to IP cameras. So here's the old CCTV rig, but that's now decommissioned, and I've just kind of quickly connected up all of the cameras so I can get the system back up and running, but it means that there's wires basically everywhere. So what I'm planning on doing is building a new server that's going to use a whole lot less power. It's going to run the CCTV as well. So if you'd like to see a video of all of that, then please leave a comment down below. And if you enjoyed this video, please give a thumbs up. If you didn't, give it a thumbs down. Subscribe if you haven't already, and thanks for watching.